So we started off and we were looking at these kind of games that Hamza was just playing, and you were just saying it was to do with the distance and the mass. And actually, if I make that a bit more mechanicsy, it's going to be the distance, the perpendicular distance, and it's going to be the force, not the mass, okay? But we know that the mass will relate to the weight, so it's still a force that we've got there. Now, I'm sure you've all got siblings or cousins, and you've taken them to the park, and you've played on the seesaw. And I'm sure if you've got little siblings, they're much smaller than you. So when you put them on the seesaw, where do you have to sit on the seesaw so that you don't send your sibling like flying up in the air? You have to sit closer to the center. And if you haven't taken your little brother or sister or cousin to the park, you should take them to the park, A, because it's nice, but B, because you can learn about moments, okay? So you should we already have this kind of experience of how things work, because just as humans, we interact with stuff around us all the time, that you have this intuition of how things behave. And what we're doing with mechanics is we're taking that intuition and we're making it become like a formal thing that we can actually make proper predictions about here. So this one's a very boring question because it's the same weight, so it would have to be at the same distance to keep it balanced. And this is also pretty obvious because it's the same distance and another one. This isn't the best of examples of games because it's only level 1. What we're going to do, though, is amp it up a bit. Now, I've got a picture of a door here before it even goes on to the booklets that I've made for you guys. Why do you think I've got a picture of a door on the board? No, actually, it's I love how cheesy that is. Yes, we're entering into a new topic. Maybe every topic should have a door. But the reason I've got a door is because of the door handle. And have you ever thought to yourself, why do we put the door handle like on the edge of the door? Why don't we put the door handle like in the middle of the door? Exactly, because it's furthest away. I know you all have trouble with opening this door and closing this door, but the door handle is always furthest away from the hinge point, okay? And it sounds really obvious, but the further you are away from the hinge point, the greater the turning force that you have. And when we talk about a turning force, that is what we mean, a moment. If the door handle was moved from here to halfway along, what can you tell me about how you'd have to pull the door? The turning force would be less, but if you wanted to open the door at the same turning force, your force would have to double, because you've halved the distance, so you would have to double. You'd have to double your force to be able to get it to turn at the same amount, right? And if you had the door handle at the hinge, you can't open the door, because you can't have a turning force, because the distance is 0, and so you'd be trapped in this room learning maths forever. So that's why we already know about moments. You've all been on seesaws. You've all opened doors. Okay, we're not quite at the stage of life where everything is an automatic door. So this is a bit more of a formal bit. Now you'll just notice for your booklets here, you don't have any textbook stuff that goes with it. I personally don't like the textbook very much for this topic. So everything is exam questions. There's a couple of bits that I've thought that are good from the textbook, but everything is exam questions on this topic. And this is only part 1. There's a part 2 booklet as well that moves it on to ladders and all sorts of things like that as well. But for now, we're just going to be starting at this area. So it says here, we previously dealt with particles, where each object was modelled just as a single point, and we considered the forces acting on each point separately. So we've done everything as dots previously. What we're going to be doing in this chapter is we consider, and this chapter is called rigid bodies, we consider rigid bodies, in this case rods, which take into account the size of the object. So no longer do we say, oh, the size doesn't matter of this object. And it says this means that we can consider other properties, e.g. the rotation of the body. So here we've got this beam that we would say is of a rod. It's of negligible thickness. And when we model something as a rod or a rigid body, we think that it's not going to bend. That's one of the properties of what it means to be a rigid body. And we'll talk about some of these modeling assumptions later. The things that I'm hoping we'll get done in today's lesson will be some stuff of all of this first bit about what moments actually are, and then some stuff to do with Actually, probably neither of these things, but we're going to do some problems that are themed around this, and then we'll hopefully get onto these in the next couple of lessons. And then afterwards, we will be moving on from things that are just flat beams, like horizontal. We'll be moving on to things that are at angles as well. Okay, so that's what the second booklet that I've made for you guys will be, and that's the stuff that has come up in both of the past papers for the Year 13 maths so far, not the flat stuff. But we need to understand the flat stuff to be able to do the angled stuff. So on the front page, I've put a little section of some key questions that sort of, if we answer these, it's kind of like a summary of what the topic is. So if you hear me sort of saying any of these things, I'll try and remember to direct you to it, but you might be able to answer some of these questions. So there's something like, what does it mean if it's uniform? What does it mean if it's non-uniform? What does it mean if it's on the point of tilting? What is on the point of tilting? What kind of language does that remind us of? Limiting equilibrium, yeah, and we've seen that with like on the point of moving. So we're going to have some similar ideas with that. Why might you take moments from different points on the beam? And there are only two things you can do in a moments question or a rigid bodies question. What are they? And so we'll have a bit of a summary of what we're looking at in this topic. Okay, so just going to have a little listen through some of these things, and then you've got a chance to do some practice in a moment. I will keep saying moment and not mean it as a joke, but moment will just happen all the time. Okay, so the moment of a force measures the turning effect of the force on the body on which it is acting. The moment of a force about a point, and this is any point that you choose, but you might get told in the question what point you're looking at a moment, is equal to the force times the distance. And it is very important that it is the perpendicular distance, because in the future we're going to be looking at some things that are at angles, and so perpendicular distance is going to become even more important at that point there.
Hi, sorry to interrupt. Sadia, do you have a receipt for me? £15.
I gave it to you. Yeah. I sent it to you. I emailed it to you.
Oh, okay.
Yeah.
The other thing, sometimes we say it's force times perpendicular distance. Another version you may see is it's the perpendicular force times by the distance. But the key thing is the distance and the force need to be perpendicular to each other. I'm mostly going to talk about force and perpendicular distance, but if you've done physics, you'll have probably seen it the other way around, that you can have perpendicular force and the distance. But I'm going to show you both. I usually settle with this idea of force and perpendicular distance. I feel like I've said the word perpendicular like 10 times, but that's good because you need to know that it has to be perpendicular to work. So we've got this particular scenario here. We've got this person on the end of the seesaw, which is 10 meters away, and they've got a weight of 700. This person on the seesaw who's got a mass of 75 kilograms and a distance of 8 meters. So we want to find out what's going to happen. So we're going to find out this one, the moment from this direction, which is trying to turn it in the anti-clockwise direction, would be 7,000. And the units, any guesses on the units? Newton meters, because it's just the force times the distance. And this one, we've got 75 kilograms, which is going to be 75 G. So the one that's trying to make it turn in this direction is 75 G times 8, which is 5,880 Newton meters. So what happens? Good, it rotates in this direction. There is an anti-clockwise rotation because we would say the resultant moment is, well, 7,000 minus 5,880. So the resultant moment is 1,120 in the anti-clockwise direction. Okay? Although I'm going to start off by talking about resultant moments, all of the scenarios we look at, whether it's to do with flat beams or ladders or things at angles, everything is always going to be in equilibrium. Okay, so we'll start off thinking about when it's not in equilibrium, but every single question we do will always be in equilibrium. If it was in equilibrium, what do you think the resultant moment would be? If it 0, yeah, you'd get the anti-clockwise is equal to the clockwise ones, so it's not moving at all. So there's a few that we've got on this page, and then you're going to do a bit of practice in just a second, I think. Tell you what, actually, you can probably find out these ones. Why don't you have a quick think? See if you can find out what the moments of these would be. I want you to tell me if they would be clockwise or anti-clockwise and what you think the moments would be. So for this first one, the force is 20 and the distance is 10. And actually, maybe I should kind of point this out for a second. I've got a piece of paper. If I put this piece of paper over the top of the board, we're talking about moments now of rotating like a flat surface. We're not talking about a beam anymore. I'm saying if I put a piece of paper over this section and I put my pen on the P point, if I push in that direction, you can see that the piece of paper is going to be turning in a clockwise direction. So we're not necessarily talking about a beam, just for the theory part at the beginning. So this is going to be a clockwise. So I want you to write clockwise, and it would be 20 times 10, which is 200 Newton meters. I'm just going to give you a few seconds to just think about these ones that you've got here, and then we'll go through them in about a minute and a half. So these are kind of like bird's eye view of a piece of paper instead.
It's not connected.
No, so what are you thinking about for this second one then? So is it, if it's here and it's just going to be pushed in that direction, is it rotating at all? No, so there's no moment at all.
But that one is like a string or something.
No, it's not a string, it's a piece of paper, and this is the pivot point, and someone is pushing it in that direction. So the thing is rotating to the right, okay? So why has this one got a moment of 0?
Because it's not rotating.
Because the distance is 0. The distance, this is the point. The distance of the force to the point, well, it's going through the point, so the distance is 0. So this one has a 0 moment, because the distance here is 0. You can talk to each other about them, you don't need to be silent here.
I think because we're too much homework nowadays, everyone's trying to be serious.
Yeah, that's what I did.
Because you what?
Everyone's got too much homework, so we don't finish it all in class. Well, I would.
You got lots of homework from other subjects?
From you.
From me?
Yeah. The whole of
The whole of which exercise? The stats one?
Yeah.
The last one that I did.
I sat down and I did do it myself. So like it doesn't take that long
Wait, you did the
To be honest, I found 12 calm.
to see if I set you too much.
I think I would have run anyways.
I don't think I set you too much. Yeah, but I don't normally teach stats. It's not my like forte, is it?
It's alright, so we're just
Unless
saying.
that homework wasn't hard, it was
It's just,
long.
yeah, that's all.
It was long.
Yeah, it wasn't hard.
Okay. Well, now that topic is tick done,
Wait, are we done with that as well?
basically.
Science is root 3 over 2, right?
Aren't you done?
You all done then?
I don't know what I'm good at.
So, okay, so here's the force that you've got like this, and we need to know the perpendicular distance here.
It's always going to rotate clockwise.
So it's going to be rotating it definitely clockwise. What's this distance here?
Why?
5 sine
5 sine 60. Good, because it's opposite the angle. So it's going to be clockwise, and it's going to be the force times by the perpendicular distance. So it's 50 sine 60. I don't care what it is. You know, it will be. So it's 25 root 3 Newton meters.
So like that one's gonna be 2 side 30.
2 sine 30. So that's the force. It's going to be going which direction? Clockwise or anti-clockwise? Good. So it's going to be anti-clockwise. And you're just going to do 10 times 2 sine 30. 2 sine 30 is 1. So it's just 10 Newton meters anti-clockwise. What's this distance here?
10m, right?
3 cos 65. So the moment is 5 times 3 cos 65, which is 15 cos 65, and it's going in that direction. Okay? So I guess I hoped that you were going to realise that I'm talking about a perpendicular distance. Now, this is weird because we're not talking about the beams at this point. We're just talking about the idea of a force and a perpendicular distance. And this is just kind of to get a bit more of the theory of how this comes together. So these, like I said before, these are all like bird's eye views of a laminar. You may have remembered, like right at the beginning of mechanics, your teacher will have said different words, modelling words. Like a laminar is like a flat sheet. So if you imagine like a... Okay. Well, if you imagine a flat sheet above these, P is the pivot point where you're doing the moments around it. So you put you're imagining that's where it's rotating around, almost like it's screwed into the board at that point, and someone's pulling it at 5 newtons in this particular angle that you've got here, and so the whole thing would want to turn in an anti-clockwise direction, okay? But the main thing I was just trying to exaggerate here is it's perpendicular distance times by the force, okay? So let's have a look at just another kind of example here that's just going to exaggerate this kind of point. So again, it says the diagram shows 2 forces acting on a laminar. And I've put a little clue thing here. A laminar is a 2D object whose thickness can be ignored. In other words, this is a piece of paper. This whole thing is a piece of paper, and there's someone on top of this piece of paper, where this piece of paper was screwed in. Someone is trying to move it in this direction, and someone is trying to move it in this direction. So it's kind of like jostling, like which way is it going to move? Is it going to turn in the clockwise direction, or is it going to turn in the anti-clockwise direction? Which of the 2 forces is trying to make it turn in the clockwise direction? The 5 newtons. So I'm going to have a look at the clockwise moment. And the clockwise moment is really easy. It's just the force times the perpendicular distance, which is just 10 Newton meters. If we have a look at the anti-clockwise, it's going to be the force, which is 8, and the perpendicular distance, which we've got here, is what? 2 sine 50, which is 16 sine 50, which is I'm just going to go 12.3 Newton meters to 3 significant figures. So what's the resultant moment?
2.256.
Good. It's just I'm just going to go 2.3 and keep it to 2 significant figures here. And in which direction? Okay, good. So that means this was the one that was winning that battle. In this scenario, this piece of paper would have started to rotate around, okay? Yeah.
Wait, how did you work out the result?
What, like?
I just did this one and this one. I was comparing them, and I did this one, take away this one. A bit like when I do resultant forces, I do those forces, take away those forces, yeah? Okay, so that's all the stuff we're doing with like laminar for now. Everything now is going back to beams and rods, okay? But I always do those at the beginning just to exaggerate. It's always the perpendicular distance. You won't worry about perpendicular distance in this first booklet. But trust me, when we get to the second booklet, when it's all ladders going against walls, everything has to be perpendicular because everything's going at a funny angle. So the things that we've got here, what I'm going to do, you won't see this if you watch this back, but the black beam that I've got here and this pivot point P, I'm saying it's like a ruler that's being held over this point here, and there are various things that are happening to this ruler. And I want to decide what is going to happen. So it's screwed in to this P point that you've got here, and someone is trying to lift it up in this direction so that it will rotate upwards. And rather than saying upwards, we always use the language of clockwise or anti-clockwise. So what's this 2 newtons trying to do? It's trying to do anti-clockwise, and this 4 newtons is trying to do a clockwise one. So you need to decide what's going to happen in this scenario. But this one's a little bit different, okay? So here, you're going to imagine that there's a ruler here and it's screwed in at this particular point. Which of these 4 forces do we have here? And I don't want anybody to say this out loud. I'm going to pick some people to think about this. So Ismail, make sure you're paying attention. Which of these 4 forces will be trying to make it turn in a clockwise direction? Just have a little think to yourself to begin with. Which of these ones do you think would make it turn in a clockwise direction, like this kind of way? Whoa, I want to pick someone. I'm not picking you, Ismail. I just wanted to make sure you were concentrating. Sufyan, what do you think? Which forces?
The 4 newtons and the 6 newtons.
Good. So this one and this one are trying to make it go in that direction. Sometimes people find this a bit tricky to spot. But if you imagine pushing that one down there and pulling that one up, it's going to make it do that. And then likewise, the 1 newtons and the 3 newtons are working together to go in the other direction. Now, the reason that, I mean, if you imagine, Sadia, if I'm pushing at 1 newtons here, it's going to make it move that way. And also, if I was over here and I was pulling downwards, it's going to do the same thing. So when you move to the other side of a pivot, the forces kind of like flip in terms of which way they are like acting. So when you move over the pivot, they reverse that direction. So I want you to decide for those 2 questions and then these following questions that we've got here, which way are the things going to move? Are they going to move clockwise or anti-clockwise? What is the overall resultant moment? If you're not sure about what I'm saying here, I'm going to do the first one anyway, and then you can have a go at the rest of them. So this first one looks like the 4 newtons is trying to make it go in the clockwise direction. So clockwise, we've got 4 times 1, which is 4. Anti-clockwise, we've got the 2 newtons and the distance is 4. So it's going to be 2 times 4, which is 8. So overall, which force is going to be winning? The anti-clockwise is bigger. So the resultant is 8 take away 4, which is 4 Newton meters in the anti-clockwise direction. So if this was a real scenario, someone's trying to pull it down, this person's trying to pull it up, they're going to win overall, okay? So you need to make a prediction about how will this one move. And then some on the next pages as well. Talk to me, Sadia. What are you thinking?
But say it's going this way, wouldn't go the same way?
So if I just put this back on the board for a second, this beam, if you imagine over here, this is exactly what the scenarios look like. It's been screwed into the wall here, okay? This force is trying to pull it downwards, but this force is trying to pull it upwards. So they're kind of fighting against each other. Yeah? So this one is trying to make it go rotating that way. This one is trying to make it rotate that way. And we're trying to say overall, who's going to win that battle? Who's got more moment power to do it? This one has got the power of 2 times 4. So it's got 8 going in that direction. This one has got 4 times 1. It's only got 4. So overall, that one's the winner. Okay? Yeah, if you've done those ones, you can start doing exercise 4B, okay, there that you've got there.
They might be 8.
Yeah.
Good point. Oh no.
You right? Yeah.
When you said the top one,
Yeah.
with the anti-clockwise thing, did you mean 2 times 3?
No, I did 2 times 4.
Oh, so the whole thing.
The whole distance. It's the distance of the force and how far away it is.
Why is the ball only times 1?
Because this force is only acting 1 meter away from the point.
Oh, okay.
It's how far away they are from the point, okay?
So you know it's a resultant, do you mean the Newton meter resultant?
Yes. Did you get that?
Equilibrium. Over. 3 plus 4. Yeah, and then anti-clock should be... Wait, am I 6 plus... Oh, 8.
Hamza is doing 6 plus 2 is 7.
No, I saw 1 too many times, that's all.
Okay, I just want to double check you've got these ones right. So this first one you should have got, it's 1 Newton meters anti-clockwise, because the anti-clockwise is 8 and the clockwise is 7. So what that really means in practice is the purple ones were winning, so it's going to turn anti-clockwise, right? But like I said earlier, ours are always going to be in equilibrium. So we're always going to just say the clockwise ones are equal to the anti-clockwise ones later on. This one over here, we've got clockwise is 20 times 10, and anti-clockwise is 15 times 10, which is 150. So it's clearly 15 Newton meters clockwise. Muzakir, out of these forces we've got here, which are the ones that are working together?
5 is clockwise.
5 is clockwise.
And 4 and 3 are working together.
So these are the ones that are working together. They're on opposite sides, but they're also on opposite sides of the pivot, so they're working together. They're trying to make it turn anti-clockwise. So anti-clockwise, we've got 4 times 1 plus 3 times 1, which is 7 Newton meters. This one's trying to make it go clockwise. So we've just got 5 times 2, which is 10 Newton meters. So overall, the resultant is 3 Newton meters clockwise. And then the last one down here, we've got 50G and 30G. So we've got 30G times 3, which is 90G, and we've got 50G times 1, which is 50G. So clearly the overall resultant is 40G in the clockwise direction.
So that's why they use crowbars.
Yeah. So you've got a few questions then that are on the next page. So you've got all of these diagrams to do. They tell you where the point P is. You've got some that are then like laminar, and you've got a few questions here. All the answers are there, and then we'll go back on to doing some actual modelling kind of questions. I'm only going to give you about 10 minutes to do these, okay?